everyone. Welcome. Thank you all for attending. It's a real pleasure to be here. Today, I wanted to talk to you guys about the future of streaming. And I think this is actually a really interesting time, as Sebastian said, because we're starting to see a bunch of different fields kind of merge together. So we have all of the richness of big data, we have the immediacy of streaming, and we're starting to see increasingly the ability to do this with the criticality of a traditional business system. So streaming really sits at the intersection of how we deal with data and how we write programs. And we can sort of describe streaming in a more contemporary sense with three separate things. It's about how we think about events, or at least how we think about programs and how we relate those back to this concept of events. It's about how we actually observe the outside world. This is a traditional concept which is known as event sourcing. And it's also about how we actually interact, how our programs interact with one another, which is about being event-driven. And if you're not familiar with Kafka, Kafka is a streaming platform, and it is at its heart a kind of messaging system. If you use messaging systems in your everyday life, you'll be familiar with this concept. But it's actually a very different kind of messaging system to the traditional ones we use. It has very good scalability and high availability properties. There are clusters with hundreds of machines, even installations that are pushing for thousands. If you go to the Netflixes, the Ubers, and the Apples, etc., it can also store very large volumes of data. There are production topics with hundreds of terabytes of data inside them. And possibly most interestingly is this stream processing piece, which allows us to blend real-time data sets from different parts of a company, from different sources, all in a single installation, or actually inside an individual microservice, and scale that elastically across different numbers of machines. So if we think about the way that we actually apply these concepts in everyday systems, if we've looked at different architectural patterns, maybe we start with something simple like a monolith, a pattern where we're effectively really just requesting data from a database, maybe doing some processing and pushing it up to a screen. And that scales its way up through distribution across multiple machines, microservices which have autonomy, and then often to this event-driven paradigm. And the reason that we tend to go to the event-driven paradigm is because we want to separate ourselves from the front end. If we start with something like a website, we might then want to progress to doing something like fraud detection, or managing a parcel as it makes its way to your door, or alternatively maybe settling payments. These are all asynchronous processes. These are processes which don't need to be tied to our user interface or our front end. So we decouple them with a messaging system. We can use Kafka for this kind of use case. And then as we extend this idea, what companies and systems tend to do is they tend to increasingly add to this back-end processing. And they do this keeping it very nicely, loosely coupled. So the architectures that tend to involve an event-driven core, where processing is done in real time over potentially large data sets that are sourced from different parts of the company, and we have a wrapping request-driven shell, which basically supports user interfaces and other kinds of lookups. But streaming is actually more than just a concept. It has at its heart this idea of an event, and an event is actually pretty important because it takes us away from this like monolithic way of thinking, where we think in mutable state, we think in databases and variables and singletons and RPCs, and move us towards this event-first approach, where we think in events, streams, logs, and stream processes. And one of the interesting things about learning to think in events is it gives us transparency to the location that we're actually in. So if we build event-driven programs, we can basically be anywhere. We might be running a microservice on one side of the world, talking to a microservice on another side of the world. And it doesn't actually matter that much, physics aside, where we're actually located. And this allows us to go on journeys. So if you're working maybe in a legacy infrastructure that's on-premise, maybe you're a financial institution that has a mainframe, you can unlock the data from the mainframe by turning it into an event stream. That actually gives you a very pure source of events. You can stream those up to the cloud, where you may maybe do fraud detection or some other use case using the nice, more contemporary tools which are available up there. And events basically let us run anywhere, on a ship, on a car, on a mobile phone, on a voyage to the cloud, all interconnecting these various separate worlds in a single real-time ecosystem. So the future in this regard sits in this concept of global streaming. If we think about the way that we integrate different pieces of infrastructure today, whether they're messaging systems or databases, what we tend to do is have multiple individual clusters spread around the world, and they kind of talk to one another with some kind of replication protocol. The future actually sits in something that's much more cognizant of this global view, something which is actually aware of the different clusters and allows us to address this global infrastructure in a very specific way, so that we can have individual topics which allow us to move events around the globe, specify where they go, maybe run different business rules. And in addition to this, should a cluster fail or a whole data center fail in one region, because we're building in this event-driven way, these will just naturally fail over to another data center, even if it's not geographically close. But events actually do more than just facilitate location transparency. They also affect the way that we observe the world and the way that we as programmers record this observation of the world. So events just seem like a pretty simple concept, right? It's just an event, it's just a fact, it's just an observation of the world, it's a payment, it's a page view, somebody hitting a website, maybe a log line in a program that you wrote, or maybe a reading from a sensor. It seems like a pretty innocuous thing, but it's actually quite a fundamental concept. Because events themselves are facts, but they tend to be represented as streams. A stream is just a collection of events that's ordered in time. It arrives one after the next. And whilst that order is important, the event records exactly what happened at a point in time. But the stream allows us to observe how a user or maybe a system actually behaved. And that's actually really important. It allows us to retain this notion of behavior. So think about something very simple, right? A shopping cart. Everyone's familiar with this concept. You might represent a shopping cart like this. You probably save it in a database like this. There's nothing wrong with that. It's a perfectly reasonable way of doing it. We've all done it. But it is actually a lossy way of storing this information. Instead, we could actually think about this in terms of what the user does. What happens when you interact with your shopping cart? So, for example, you might add 2 pairs of trousers, then you add a jumper. Then you realize that you didn't really want 2 pairs of trousers, because who wants 2 pairs of the same pair of trousers? So you remove one of them, and then maybe you add a hat, and then you check out. So the events actually journal exactly what you actually did as a user. So in streaming, we observe these events. So we observe the world, we keep the observation as an event stream, and then we apply a projection which turns it into the shape that we want, maybe back to the shopping basket that we're actually going to display on the user screen. So the current state is just a projection of the observed behavior. So on the left-hand side, we have the events, ordered in time. We can extract behavior from them. Over here, we have the stateful view, which we might put in a database, where information has been lost. We can always derive one from the other with something like a stream processor. There's obviously no way you can go the other way, right? If you start with this, you're not going to get that. Actually, technically, that's not true. If you use a database, you can use a special kind of connector which extracts events, but that's a different topic. So we want to capture the world one event at a time and observe this underlying behavior, and particularly leverage this in use cases where the underlying behavior is super interesting. So if you think about something like a chess game, you'd never describe a chess game as being the end state where you happen to get the rook in a position where it's in checkmate. You're much more interested in this idea of actually how the game evolved over time. And this is true for lots of different types of data. This is true for stock prices. It's the evolution of the stock price which is interesting. It's true for a customer journey, how a customer actually interacts with your website, with your company, through all of these different points, which is one of the reasons streaming is very popular for Customer 360. It's also true for Formula One. So Formula One, you might think, is just about optimizing this end state, who's at the top of the board. But the actual act of winning at Formula One is about optimizing how we actually get there. So I like this use case, so we're going to dwell on it a little bit more. So Formula One race obviously involves a car. The car's got about 400 sensors on it. Lots of different instruments on the tires, on the measuring temperature, measuring suspension compression. And these all get streamed off the car. And this isn't actually a big data use case. Big data use cases, we'd look at Netflix and Apple, etc. But this is a fast data use case. We know it's not a big data use case because it's actually being streamed over a radio frequency, over a radio link. In fact, it's exactly the same frequency that you use for like a remote control car. So this actually gets streamed back to a truck. The truck has a small data center installed on it with a little 3-node Kafka cluster. And the truck basically gets shipped around the world from race meet to race meet, where it does all this streaming. And it streams this data back across the internet to the headquarters, which is typically in a different country. And there, a bunch of stream processors run. And these stream processors do a number of different things. They do some quite simple things, like correlating different events together in time, like the temperature of the tires, the pressure of the tires, the suspension compression. They also run physics models. The physics models are very useful for modeling the aerodynamics of the car. And they also use machine learning models to do things like help with racing line and a few other things. It turns out that actually machine learning is pretty hard to do in something like racing because you have to have some data to train the machine learning model with. And the car's basically being changed all the time, so your back population of data doesn't really work in this black box model. It's one of the reasons they use physics models quite a lot. But you can do it. So we have all of it. Once we've got all this information, it goes to the performance engineer. The performance engineer feeds this back to the driver, works out how many pit stops they want to have, advises him on things like setting his engine mode and his racing line. And then hopefully he wins. But at the end of the race, we need to do some post-race analysis. So maybe something went wrong in the race, we want to go back in time and look at what happened, or maybe we want to try tweaking the various physics models, etc., and seeing if we can improve things. We could build a completely separate system for doing that, but that would be kind of wasteful. Because at the core of this streaming system, at the core of this flow of events, sits Kafka recording everything that happened. So we can take our real-time stream processing engines, and if we want to look at something retrospective, we simply rewind him back in time, and we replay for the bit of time that we're particularly interested in. Maybe changing the model on the way if we want to. So this is really another form of event sourcing. We record everything as immutable events. We change our projection if we need to, and then we rewind and replay in order to reevaluate. So this is actually also applied in various different business domains, very different to the kind of traditional streaming ones. So this is the architecture of the New York Times website. It's a content management system, essentially. Data comes in on one side, it gets pushed into this single Kafka topic. They call it the monologue. And that has every single article since 1851. In fact, it has actually every single image, every single byline, every single tag, every single piece of text. And each one is normalized and arranged as a separate message. They then use a stream processor, this denormalizer in the middle, and that turns that canonical source of truth that's constantly evolving in time as they add new content into a set of views. And these views represent what they actually want to show on the website at any point in time. So if they want to change the look and feel of the website, if they're going to go through a new release, some kind of radical redesign, all they actually need to do is change this stream processor, replay the views, a new set of views get created in these serving layers over here, and then get accessed by the front end. So this idea that we can basically retain data sets, apply projections, and then use them to do new and interesting things is actually applied in a number of other use cases, which basically make data much more self-service, allow us to get make it very easy for a new application. So say you're building a new fraud system or a new reporting system or a new analytics system, or maybe just something that sends emails. So a number of companies have something like this, and I think we'll see more of this in the future. So you have like a central console. The console basically shows you all of the information in the company, all of the streams. You can search the schemas. You can see how much data is inside each topic. You can see how fast this data is moving. You can select maybe a couple of things that you're interested in. Here I've just picked orders and customers. And then I'll actually specify how much data I'm interested in. So maybe a week of orders, but I want all the customers because I want to be able to look up their email addresses. And then push that into a stream processor. This creates the projection. So this whittles down the data to exactly the thing that I actually want. And then I might spin up a new instance of Elasticsearch, populate this data, or alternatively, because we're actually driving from events and what we're ending up with is nice enriched events, I can push that into something like a microservice or a Lambda function. So the point of doing this is really to get us to a point where data is very self-service, where it's very easy for you to be able to spin up some new application for some new requirement that you get asked to serve and answer it very quickly. But the cloud is probably the next thing that's most interesting. And evolving to the cloud actually changes the game. And this relates, I think, to stream processing in quite an interesting way. There's actually lots of interesting things about the cloud. And I'm actually going to talk very specifically about one. I wanted to talk about stream processors and then particularly this notion of functions as a service. People often call this serverless, although serverless is actually something that was defined a little bit earlier. So if we use a serverless architecture, if we use functions as a service, we have this very simple approach to writing a program. For a start, it's event-driven. So it's a bit like streaming. It's driven from events. And we basically just write a function. There's a set of different languages, Java, Node.js, a few others, that we can write a function in. We then upload that, and we configure some kind of trigger. That might be an HTTP call. It might be an event. It might be a write to a database or an object store. It might be something that's triggered from a timer. And FAS is kind of interesting because it's a pretty different programming model. These functions can only run for a fairly short amount of time. They're actually running inside a small container. You don't know anything about this because you're completely abstracted away. And you pay only for as long as the invocation takes. The other interesting thing about FAS is it provides a lot of elasticity. Because it's basically pay-as-you-go like your mobile, you could have no functions running at all, and you would pay nothing. Alternatively, if you get an influx of load, you can scale out to like 1,000 different machines, or at least 1,000 different functions running concurrently. So this opens up some interesting new possibilities. So we can think about this from the point of view of doing things like image processing. We can think about the point of view of doing sort of simple analytics tasks. I actually think one of the most interesting uses of FAS is actually in the things that we would never think to use distributed computing for. So for example, your build system. It's like, how long does your build, how long does your continuous integration system actually take to run? Maybe it takes 10 minutes, maybe an hour, depends on what you do. But with something like FAS, that kind of spiky workload and very simple implementation style means that you can do something like run across 1,000 different machines. So that's going to divide your build time by 1,000, give or take. The startup time on these things can be leave a little bit to be desired. So the way FAS actually changes the way that I think about the world, is that it allows us to use some of these distributed systems concepts in areas that we probably wouldn't before. Like our core business systems, we might use Kubernetes because we care enough about that part of the ecosystem to put the effort in. But the periphery stuff is definitely very interesting. But it's actually a little bit more than that. So there are a number of open questions about FAS. Camille Fournier wrote, I wonder if serverless services will become a thing like stored procedures, a good idea that quickly turns into massive technical debt. And this is kind of an interesting idea, right? You're pushing a function up to the cloud, and it's like, do you actually know what it's doing? It's a bit like a stored procedure. Maybe you know when it's running, maybe you don't. And I think this is actually quite an interesting point. So currently, runtime diagnostics, monitoring, testing, IDE integration, they're okay, but they're not great. But the interesting thing is it will come when these things are really good. So when we're able to run a serverless function that has excellent runtime diagnostics, has excellent monitoring, is really, really easy to test because you can distribute your testing very easily, has a wonderful IDE integration that makes it really easy for you to run these functions on this platform, that would be really interesting. We definitely never got that with stored procedures. But would that ever happen? Well, there's actually this tipping point where as these ecosystems get more advanced, and the reason that I actually think this is quite likely to happen is that 3 of the biggest companies in the world really, really, really want you to use this technology. And you can read into that what you will. So Amazon, Google, and Microsoft, very interested in these, in functions as a service, because it definitely serves their purpose. But Sam Newman, who wrote the book on microservices, also made an interesting comment, which is people who think serverless will solve all their problems will end up sticking all of their crap in one giant database. And this may or may not be true, but it kind of brings me to my next point. FAS is event-driven, but it's not really streaming. Right? So if we think about how a FAS implementation works, each function can be driven by an event stream, but only one. When we execute that function, if we need data from different places, let's say we have data coming from a customer service, an order service, and a payment service, and we want to pull together the payment and maybe the user's email address and send an email, we have to reach out to these different databases. This is an event-driven design, and there's nothing specifically wrong with it, it's just not streaming. In the streaming way, we are event-first, event-sourced, and event-driven. So we would take the same data sets, the same streams, and push them into a stream processor. The stream processor is able to do the buffering to deal with the asynchronicity of the orders and the payments. It's able to materialize a table which allows us to look customers up in real time. It's able to scale this over any number of machines, with the loads, balancing the load across each instance. And possibly most importantly, certainly in the future, it's able to do this all with transactional guarantees, actually the same transactional guarantees you get in a database, implemented in a very different way, I must add. So the interesting thing about FAS and stream processing is that they kind of complement one another. If we think about one of the side effects of stream processing, or at least stateful stream processing, it doesn't have to be stateful, is that it often ends up with state. So if we're buffering events, that's state. If we have tables, that's state. If we create new tables, which actually are written back to Kafka, that creates more state. So although we can run these stream processors in a stateless way, we often want to run it in a stateful way, so that we can bind these rich data sets together and create effectively larger events which have all the information that we need. And then we could push those into a serverless function. So what we would be leveraging on this side is the statelessness, the beautiful elasticity, and maybe in the future some really nice IDE integrations and some nice monitoring and some nice runtime behaviors, etc. So this is kind of an interesting idea. Another interesting idea is that to take this transactionality that comes with the stream processor and push it into the FAS domain. This would actually take a little bit more work. So again, very similar transactions in Kafka are very similar to those you'll see in a database. They're actually inherited from Kafka itself, but they just have a different implementation. So if we go down this line of thinking, what we end up with is a traditional application everyone's familiar with. Stateless, states held in a database. We ask the database questions. Event-driven application, driven by a single stream of events, calls out to different services or different databases to bind data together. A streaming application does all of the joins in real time, never pauses, is never punctuated, but is often stateful, often has some notion of state. And then maybe we'll push into a stateless layer. So this is actually often done with stream processors, the stream processor replacing the FAS layer, but obviously we could also do it with FAS, with a bit of tweaking. So the interesting thing is that we actually have this model kind of turned on its head and applied over here, with the data coming in as events, being enriched and processed, and then pushing to a stateless application there. So you basically would put your business logic in here, much like you would in a traditional architecture. So, in summary, I think streaming does a number of different things. It changes the way that we think, because it makes us think about events first, both in the way that we model our business and our problem, as well as the way that we actually drive functionality. So we build in events first, and then think about including pieces of state, doing lookups, etc., etc. Event source, which is about how we observing the world in a way that we see everything, and only add a projection which brings it down to the more traditional stateful representation which we might like in our programs. And event-driven, which is about how we actually interact with the world, how our programs interact with one another, driving things forwards and being real-time. So when we bring these ideas together, we have global systems which have location transparency. We have the ability to store information about everything that our customers do, everything that our IT architecture does, stored in a single platform and processing implemented using these often cloud-native stream processors, certainly in the future. And that's all I had to say. Thank you very much for listening. It's a real pleasure to be here. If any of these ideas resonated with you in any particular way, I actually wrote a book on this subject. There will be a book signing, I think, in the break later, and there's a few copies. You can get a copy if you want. You can also get it online if you prefer. And yes, thank you very much for your time.